In question 1, we've got the beam AB with a weight of 24 newtons and a length of 6 meters. We are suspending the beam through 2 light vertical ropes shown here. We've got the distance as x meters, the distance AC, and 2 meters, the distance CD. We are told that the tension at C is double the tension at D. We are modeling the beam as being a uniform rod resting horizontally in equilibrium, and we need to find the tension in the rope attached to the beam at D and the value of x. So the first thing to do is add all the forces acting here. We've got the weight of 24 newtons at the middle. We've got the tension at C and the tension at D. And we know that the distance between A and the center of mass is 3 meters because we are assuming we are modeling the beam as being uniform, which means that the center of mass is at the midpoint. So we have also been told that the tension at C, so TC, is twice the tension at D, so it's equal to 2 TD. So we can say that for this to be in equilibrium, the forces acting upwards must be equal to the forces acting downwards. So we've got TC plus TD is equal to 24. Now we know that TC is 2 TD, so 2 TD plus TD is equal to 24, leading to 3 tension at D is 24, and therefore the tension at D is equal to 8 newtons. To proceed and find the value of x, I will first start by finding the tension at C. So we know for sure that the tension at C is twice the tension at D, so it's 2 times 8, which is 16 newtons. And therefore I can proceed by taking moments about A. So we've got that the clockwise moment is the 24 newtons acting at a distance of 3 meters. So we've got 3 times 24, which is equal to the anti-clockwise moment, which is x times TC plus x plus 2 times the TD. We know TC and TD, so 3 times 24 is 72, which is equal to 16x plus 2 times the TD, which is 8. I will expand the right hand side to get 72 is equal to 16x plus 8x plus 16. This leads to 56 being equal to 24x, and therefore x turns out to be 7/3. In question 2, we've got the acceleration time graph representing the motion of a car traveling between A and B. So we know that at t0 the car is passing through point A with a speed of 8 meters per second, and at time t is 20 is passing through B with a speed of v meters per second, and we need to show that v is equal to 18. Well, we know that the area under the acceleration time graph is the overall gain in velocity, and I'm going to use exactly this fact to determine the gain in velocity as I move from A reaching B. So let's calculate the total area. We've got this part here, which is going to be 4 times negative 0.5. Then we've got a contribution of 0 between 4 and 10. So let me write plus 0 plus the 10 times the 1.2. So 10 times 1.2 is the final area there. If I add everything up, I get an answer of 10. We were passing through A with a speed of 10, and therefore the speed as we pass through B, it's going to be 8 plus 10, which is equal to 18 meters per second as required. In part B, we need to sketch a speed time graph for the motion of the car from A to B. So we've got the speed and the time. Speed is always positive, so we will be drawing something that's entirely on the positive vertical axis. We started off with a speed of 8, we were decelerating, then we maintained a constant speed, and finally we were accelerating. So the graph looks something like this. We know that the initial velocity was 8. We know that after 4 seconds we have dropped by 2 meters per second in speed, so we're now at 6. We have maintained the speed of 6 for the time of 4 up to 10, and then at 20 seconds we're traveling at a speed of 18. So this completes the speed time graph. Now to proceed and find the distance AB, I simply need to find the total area under the graph. So we're looking at a trapezium, a rectangle, and another trapezium. I simply need to add up the areas here. So the distance AB, it's gonna be the 8 plus the 6 over 2 times 4. I'm applying the formula for the area of the trapezium here. So base 1 plus base 2 over 2 times the height plus the rectangle, which is 6 times 6. So let me write this down, 6 times 6 plus the area of the final trapezium here. So it's going to be 18 plus 6 over 2. So 18 plus 6 over 2 times the height of 10. If we plug this on the calculator, we get an answer of 184 meters, which is the distance AB. In question 3, a hammer is used to hit a peg into soft ground. The hammer has a mass of 1.8 kilograms and the peg has a mass of 0.2 kilograms. We are modeling both of these as particles and the impact is modeled as a direct collision. So we are told that initially the peg is stationary, the hammer is moving with a speed vertically downwards of 10 meters per second, and immediately after the impact both the hammer and the peg move together with the same speed of v meters per second, and we need to find the value of v. So it makes sense to draw a diagram. We've got the hammer and the peg, the masses are there. Now before the collision we had the hammer moving downwards with a speed of 10 meters per second, whereas the peg was stationary, so the speed is 0. And after the collision they are both moving downwards with a speed of v meters per second. So I can proceed with conservation of linear momentum. We can say that the momentum before was 1.8 times 10 plus 0.2 times 0, which is equal to 1.8 v plus 0.2 v. So we're looking at 18 being equal to 2v, and therefore v is equal to 9. In part B, we need to find the magnitude of the impulse exerted on the peg by the hammer, stating the units of our answer. So we will be considering the peg. We know that the impulse is the change in momentum, so the impulse I, it's gonna be the momentum after, so 0.2 times 9 minus 0.2 times 0, that's the momentum before the collision. This gives an answer of 1.8 and the units are Newton seconds. And in part C, we are told that the ground exerts a constant vertical resistive force of magnitude capital R newtons, bringing both the hammer and the peg to rest. After traveling a distance of 12 centimeters, we need to determine the value of R. I will draw a diagram here. This is the combined mass of 2 kilograms. We are traveling downwards, so I'm always putting my acceleration pointing towards the direction of travel. We surely have the weight of 2g pointing downwards, but then we also have this resistive force of capital R, and the objective is to find this capital R. I will start by stating that the initial velocity of this combined system is 9 meters per second. It's being brought to rest, so the final velocity is 0 meters per second, and the displacement, the distance covered, is 0.12 meters. Be careful here because we were given this in centimeters. We need to make sure that there is homogeneity in the units, so I'm gonna convert the centimeters into meters. I will then be using v squared is equal to u squared plus 2as, so 0 squared is equal to 9 squared plus 2 times a times 0.12, leading to 0 being 81 plus 0.24a, so minus 81 is 0.24a, and this gives an answer for a of negative 337.5. So it comes as no surprise that the acceleration is negative because the whole system is decelerating, and therefore we can proceed with the equation of motion for the 2 kilograms here. It's traveling downwards, so I'll be doing forces acting downwards minus forces acting upwards is mass times acceleration. So we're looking at 2g minus r is equal to mass times acceleration. So 2 times 9.8 minus r is equal to 2 times minus 337.5. So this leads to 19.6 minus r is equal to minus 675. So if I collect the numbers on the left hand side, I get 694.6 for the value of r. Obviously, if I leave this as my final answer, I will be penalized because it is at 4 significant figures. We need to be giving answers to 2 or 3 significant figures because we have used g to be 9.8. So my final answer for r will be 695. In question 4, for the particle p moving with a constant acceleration of negative lambda I plus 2 lambda j, lambda is a positive constant. At time t0, the velocity of p is 5I minus 8j, and we need to find the velocity of p when t is 5, giving our answer in terms of I, j, and lambda. Well, we know that the velocity v is given by u plus at. So in our case, the u, the initial velocity, is 5I minus 8j. The acceleration is given to be negative lambda I plus 2 lambda j, and the time is 5. So I will combine everything together. We are looking at 5 minus 5 lambda I plus the minus 8 plus 10 lambda j, and all of this is the velocity, so it's meters per second. We're then told that the speed of p when t is 5 seconds is 13 meters per second, and we need to show that this leads to this quadratic in lambda. Well, we know that the speed is the magnitude of velocity, so I will be calculating the magnitude of the velocity vector we obtained in part A. So we're looking at 5 minus 5 lambda all squared plus negative 8 plus 10 lambda all squared and all square root being equal to 13. Now the first thing to do is remove the square root, and this will give me 13 squared on the right hand side, and on the left hand side I will start expanding. So we're looking at 25 minus 50 lambda plus 25 lambda squared plus 64 minus 160 lambda plus 100 lambda squared. I will be collecting like terms on the left hand side. We've got 125 lambda squared plus 89 minus 210 lambda being equal to 169, and all of this leads to 125 lambda squared minus 210 lambda minus 80 being equal to 0. The next thing to do is divide everything by 5, and I get 25 lambda squared minus 42 lambda minus 16 is equal to 0 as required. And in part C, we need to find the direction of motion of p when t is 4, giving our answer as a bearing to the nearest degree. Now the direction of motion is stemming out of the velocity, so the first thing to do is go back to the quadratic in lambda, solve it, get the value of lambda. So this quadratic factorizes into 25 lambda plus 8 times lambda minus 2 being equal to 0. So we get 25 lambda plus 8 is equal to 0, or lambda minus 2 is equal to 0. Now we get the lambda is negative 8 over 25. I will reject this, it's not valid since lambda has been given to be positive, so it's rejected, and we end up with lambda being equal to 2. So I will be using v is equal to u plus at. So the velocity is given by the initial velocity of 5 negative 8. The acceleration was negative lambda 2 lambda, so it's gonna be negative 2 4, and the time is 4. So 5 plus negative 2 times 4 gives me an answer of negative 3, whereas negative 8 plus 4 times 4 is 8, so the velocity is negative 3, 8. Which means I can quickly draw a sketch to see what's happening. This is the vector negative 3, 8. We go 3 to the left and 8 up. We're trying to find the bearing. So from the initial point here, I draw the north and I turn clockwise. I'm trying to find this angle here. It makes sense to find the angle theta here, and then using alternate angles, I will find theta there and deduct that from 360 to get the bearing. So we're looking at tan theta being equal to 3 over 8. This leads to theta being equal to 20.556 ... and therefore the bearing is going to be 360 minus 20.556 ... This gives an answer of 339 degrees to the nearest degree. If you give more accuracy here, you will be penalized. In question 5, we've got a small ring of mass 0.2 kilograms attached to one end of a light inextensible string. The ring is threaded onto a fixed rough vertical rod. The string is taut, making an angle theta shown here. We know that tan theta is 12 over 5, and we need to find the magnitude of the frictional force acting on the ring, given that the ring is in equilibrium and the tension in the string is 10 newtons. So the first thing, as always, is to add the forces on my diagram. We start with the weight of 0.2 g. We've been told that the tension is 10 newtons. So I will be resolving my tension in a vertical and horizontal direction. So the horizontal is 10 sine theta and it's pointing to the right, and the vertical is 10 cos theta pointing upwards. We also have a reaction to balance out the 10 sine theta pointing to the right. So we can also proceed with tan theta being 12 over 5. So I'm drawing a right angle triangle. This is 12 and this is 5. So it's a 5, 12, 13 triangle. So sine theta is 12 over 13 and cos theta is 5 over 13. The only force missing is the friction. It could be pointing downwards or upwards depending on whether the ring is about to go up or down. I'm not going to put it on my diagram yet. I will just proceed finding the numerical value of 10 cos theta and comparing this with 0.2 g to decide in which direction the friction should be pointing at in order for the things to balance out, in order for the system to be in equilibrium. So we've got 10 cos theta being equal to 10 times the value of cos theta, which is 5 over 13. This gives an answer of 3.846 ... newtons. On the other hand, the 0.2 g is equal to 0.2 times 9.8, which gives an answer of 1.96 newtons. So obviously the force pointing upwards is greater than the force pointing downwards, so the friction must be here, and for the ring to be in equilibrium we must be having that the 3.846 ... is equal to 1.96 plus F, and this leads to F being 1.89 newtons. I'm giving my answer to 3SF because I've used G to be 9.8. In part B, we need to state the direction of the frictional force, and based on all the work we've done in part A, it's obvious that the direction is pointing downwards. We are then told that the coefficient of friction between the ring and the rod is 1/4, and the ring is in equilibrium with the tension now varying. We need to find the minimum value and the maximum value of this tension. So I will be considering two separate cases. When we are looking at the minimum tension, this is a situation the ring is about to go down, so the friction is opposing this motion, so we've got the friction pointing upwards. Whereas for the maximum tension, it's exactly the opposite. We've got the friction now pointing downwards because the tension is so much that the ring is about to go up, and therefore the friction is opposing this, so the friction is pointing downwards. I will start by stating that in both cases the reaction is T sine theta, so it's gonna be 12t over 13. Remember, we found sine theta to be 12 over 13 from the triangle we drew in the previous parts. We also know that the maximum friction F max is gonna be mu r, and in both cases, since we're looking at the minimum and maximum value of T, we are attaining this maximum frictional force. So in our case, this is gonna be 1/4 times 12t over 13. This simplifies to 3t over 13. It's going to be the friction in both cases. The only thing that's changing is the direction of the friction. So for the minimum value of t, we've got that t cos theta plus F is 0.2 g. So we're looking at 5t over 13 plus the friction of 3t over 13 being equal to 0.2 g, leading to 8t over 13 being equal to 0.2 g. I will be cross multiplying to get 8t is equal to 2.6 g, and if I divide both sides by 8, I get t to be 3.185. I will be giving my answer to three significant figures. So the minimum value for the tension, I'll call it T mean, is going to be 3.19 newtons. Now for the maximum value, we've got that T cos theta is 0.2 g plus F. So let me write this down. T cos theta is 0.2 g plus F. So we're looking at 5t over 13 is equal to 0.2 g plus 3t over 13. So I get 2t over 13 is equal to 0.2 g. Again, I cross multiply to get 2t is 2.6 g. If I divide both sides by 2, I get that t is 12.74. So the maximum value for the tension is going to be 12.7 newtons. In question 6, we are told that the ship P sets sail at 1200 hours from a harbor with position vector 15i plus 36j. Half an hour later, it's at 20i plus 34j. It's moving with constant velocity, and we need to show that the velocity is 10i minus 4j kilometers per hour. Well, we know that the position vector we are at any given point is equal to the initial position vector plus the velocity vector times the time t. Since we have no acceleration, the acceleration is 0. We're traveling with constant velocity. This is the formula for the position vector in terms of t. So we know that half an hour later we were at 20i plus 34j, and this is equal to the initial position vector of 15i plus 36j plus the velocity vector that we're trying to find. I'll call it u times a half. So we're looking at 5i minus 2j is equal to a half u. So if I multiply both sides by 2, I get 10i minus 4j is equal to u as required. Now at time t hours after 12 o'clock, the position vector of P is P, and we need to find an expression for P in terms of I, J, and T. So once more, the position vector of P will be the initial position vector of 15I plus 36J plus the velocity we just obtained of 10I minus 4J times T. I can group the I's together, so we're looking at 15 plus 10t I, and I group the j's together. I've got 36 minus 40 j. This is the position vector of P at t hours after 12 o'clock. We then have a second ship Q also traveling at a constant velocity. This is the position vector in terms of t hours after 12 o'clock for the ship Q. Now we're modeling both as being particles and they are maintaining their course. We need to verify that they will collide at 1:30, and we need to find the position vector at which the collision will occur. Well, we know that at 1:30 we're looking at t being 1.5 because we are 1.5 hours after 12 o'clock. I will be finding the position vector of P, which is going to be 15 plus 10 times the 1.5, and that's going to be my I component. And then for the J component, we're looking at 36 minus 4 times 1.5, and this is the J component. Now this simplifies to 30I plus 30J, and what I'm expecting is that if I do the same for Q, I should be finding exactly the same position vector. So we are pretty much saying that when t is 1.5, they will be at the same place, so they will be colliding. So the position vector Q is going to be 42 minus 8 times 1.5. That's the I component. And for the J component, we're looking at 9 plus 14 times 1.5. So as expected, this is giving me 30I plus 30J, which means I can safely conclude that since P is equal to Q, the two ships will collide at the point 30I plus 30J. We're now told that at 12:30 Q changes speed and direction to avoid the collision. So ship Q is now traveling due north with a constant speed of 15 kilometers per hour, while ship P maintains the same constant velocity throughout. And we need to find the exact distance between P and Q at 2:30. So we need to be careful here, since we've got a change in direction by one of the ships at 12:30. We need to reinitialize the time being 0 at 12:30. So for ship P, we've got that the position vector is the initial position vector at 12:30, which we were told to be 2034, plus the speed, which is maintained at 10⁻⁴ times t. So this is 20 plus 10t, 34 minus 40 is the J component. So Be careful here. T is the time after 12:30, and I will repeat the process for shape P. So I will start by stating the obvious, that the new velocity of Q is simply 0.15 because we are going 15 upwards, and at 12:30 I will find the position vector of Q. So we had T is equal to a half, which means that the position vector of Q at 12:30 is 48 minus 8 times a half, and 9 plus 14 times a half. This gives an answer of 3816, which is gonna be my initial position vector for the new time frame. So if I now consider the new position vector of Q, where T is now the time after 12:30, it's gonna be 3816. It's my initial position at 12:30 plus the new velocity vector of 0.15 times T. So this gives me 38 for I and 16 plus 15T for J. We are trying to find the distance at 2:30. So at 2:30 we know that the time is gonna be 2. So I will be replacing this for both RP and RQ. So RP, it's gonna be 20 plus 10 times 2, and 34 minus 4 times 2. This gives an answer of 40 and 26, and I'll do the same for RQ. So the position of Q at 2:30 in the afternoon, it's gonna be 38 and 16 plus 15 times 2. This gives an answer of 3846. The only thing missing is to find the exact distance between the two ships. So the distance PQ, it's gonna be the difference in the I component square plus the difference in the J component square, and all square root. So it's gonna be 40 minus 38 squared plus 26 minus 46 squared, and all square root. This gives an answer of 2 root of 101, and that's kilometers. In question 7, we've got a block A of mass M resting on a rough plane. It's inclined at an angle alpha. The coefficient of friction is mu. We've got one end of a light inextensible string attached to A, passing over a small smooth pulley fixed at the top of the plane. That's the pulley here. The other end is attached to the block B, having a mass of km. Now the string is taut. The string from A to the pulley lies along a line of greatest slope of the plane. We are modeling both A and B as particles, and when we release the system from rest, A goes up and the tension is 4 mg over 3. Additionally, we are told that mu is 1 over 3 and tan alpha is 7 over 24, and we need to find the magnitude of the acceleration of A, giving our answer in terms of g, as well as the value of k. Obviously, for a 9-mark part of the question, I will be spending some time to add all the forces acting here. So we've got the weights of kmg and mg. We've got the tension at B pointing upwards, the tension in the string at A pointing up the plane. We will be resolving the weight of mg, so it's going to be mg cos alpha perpendicular to the plane and mg sine alpha down the plane. Obviously, we've got a reaction, and the whole system is accelerating with A moving upwards and B going downwards. So we've got the acceleration pointing downwards for B and up the plane for A. This means that the friction is opposing motion, so the friction is here. So we've got all the forces here. We can also quickly draw a right angle triangle to find sine alpha and cos alpha. We've been told that tan alpha is 7 over 24. So it's a 7, 24, 25 triangle, which means that sine alpha is equal to 7 over 25 and cos alpha is equal to 24 over 25, so that we can proceed in finding the magnitude of the acceleration of A, giving our answer in terms of g. So we will start by considering A. We've got vertically r being equal to mg cos alpha. So let me write this down. R is equal to mg cos alpha. And we know that cos alpha is 24 over 25. So we're looking at 24 mg over 25. Now the friction is attaining its maximum value, so it's equal to F max, which is equal to mu R. In our case, mu has been given to be 1/3. The reaction is given to be 24 mg over 25. This simplifies to 8 mg over 25. This is the frictional force, and I can proceed with the forces acting up the plane minus forces acting down the plane, being mass times acceleration. So we're looking at T minus mg sine alpha minus F is equal to ma. We're trying to find A here. The tension has been given to be 4 mg over 3 minus 7 mg over 25 minus the friction of 8 mg over 25 being equal to ma. We notice that there is a common factor of m which I cancel out, and if I collect all the terms on the left hand side, we get that the acceleration A is 11g over 15. Remember, we had to find the acceleration in terms of g. If I proceed in finding a numerical value, I will be penalized. Now, to find the value of k, I will be considering the particle b. We've got forces acting downwards for b, which is kmg minus the tension T is equal to kma. Well, kmg minus the tension, which is 4 mg over 3, is equal to 11g km over 15. I'm using the value we just obtained for the acceleration. We now notice that mg is a common factor, so I will cancel this out. This leads to k minus 4 over 3 is equal to 11k over 15. I will be multiplying throughout by 15 to get that 15k minus 20 is equal to 11k. We get that 4k is equal to 20, and therefore k is equal to 5. For part B, we need to find the magnitude of the resultant force exerted on the pulley, giving our answer in terms of M and G. So if we imagine what's happening at the pulley, what the pulley is feeling, it's feeling two tensions, one on either side of it. So the resultant on this will be along the angle bisector at the pulley here. So this is going to be the resultant here. I will be calling this angle theta, and there is a general rule that the force exerted on the pulley by the string is given by 2t cos of theta over 2. Now we have established, we have been given that t is 4 mg over 3. So what's happening with theta? Remember, the angle at the base here was alpha, and we knew that tan alpha is 7 over 24. This means I can proceed in finding the actual value of alpha. It turns out to be that alpha is 16.2602 ... and therefore theta, which is 90 minus alpha, is going to be 90 minus 16.2602 ... leading to 73.7397. This means that the force exerted on the pulley, it's going to be 2 times the tension of 4 mg over 3 times the cos of theta over 2, so cos of 73.73 ... over 2. I'm maintaining full accuracy on my calculator, and this gives an answer of 32 mg over 15 newtons for the force acting on the pulley by the string.